circles and for loops. So here's another pattern, and I'd like you to pause the movie and write down what you see. How would you describe this pattern? What are the specific attributes of the components of the pattern that we might want to capture? That is, what sorts of values are changing to generate this pattern? How would you program this pattern? So pause the movie, have a go at writing this down. Well, we see a series of 3 concentric circles, don't we? Which appear to be stacked or layered, with the biggest circle at the bottom, the medium-sized circle in the middle, and the smaller circle on top. So they're actually centered on 100, 100, and their diameters seem to decrease in a regular fashion. They actually decrease from 120 to 90 to 60. Although I wouldn't expect you to be able to work out the specific values from the graphic. It's enough for you to notice that they decrease regularly. And the other thing to notice is that they're filled in with a shade of green that seems to get increasingly bright or more intense as the diameter increases. So the larger circle is less intense, if you like, and the smaller circle is brighter. So there's an inverse relationship between the diameter of the circle and the radius of the circle. So why do we start with the biggest circle? Well, obviously they're drawn on top of each other, so if you draw the bigger objects, increasingly bigger objects on top of one another, they'll overwrite. So we start with the layers. We start with the biggest circle first, and then work that way. So how would we start to express this in some sort of algorithm, in some sort of pseudocode? Well, we may say something like this. If we assume that we keep track of some variable called diam, for diameter, we might say something like, for circles with diameter between 120 and 60 in steps of 30, so we're going down from 120 to 60 in steps of 30, change the fill and stroke color to some sort of green that's been modulated by the size, by the diameter, and then draw a circle at 100, 100 with its center at 100, 100 with the diameter of that diam. So you're essentially saying for values of some variable diam between 120 and 60 in steps of 30, so you're going down from 120 to 60, draw a circle that looks like that. Okay, so we can see how we can not only directly use a diam counter, if you like, to change the diameter of the circle being drawn, but also indirectly to alter the intensity of the color. And this is important because we might naively maybe come up with a separate way of tracking the color, a separate variable to keep track of the color, but there's no need, because in this case the intensity of the color is linearly related to the diameter of the circle. So we can easily derive the color from the diameter by just subtracting the diameter from some upper value. Okay, so essentially the algorithm is for circles between 120 and 60 in steps of 30, draw a circle with that diameter. Now, how do we actually go about implementing this in processing? Well, we have this idea of, for values of some variable, let's call it x, or diameter, or whatever, the range of which is a to b, and it moves in steps of d, we can formalize this in processing using the for loop. So we use it for iteration where we know in advance how many times we want to loop. So all the examples we've seen so far in this category fall into this category, like 13 lines and 3 circles and so on. So let's just go back to these lines and see how we would implement the algorithm in processing. So remember, the pseudocode basically says for values of some counter x running from 20 to 140 in steps of 10, draw a line from x20 to x180. Okay, so here's the algorithm, here's the code, and hopefully you can see the correspondence. but it will be made much more clear if I do this. Okay, so we have the declaration, if you like, of the for loop here. It sort of sets up the loop, it specifies the start and end point and the stepping, and then the actual thing that we want to do within the loop, which is to draw the line based on the values encoded in the loop. So here's the declaration of the sort of structure of the loop, and here it is here in the code, and here's what we actually want to do inside the loop. Draw a line from x20 to x180, and here you can see a fairly close correspondence in the processing code. So let's look at this in more detail, and we'll deal with the loop body first, as it's the most straightforward. So we have some variable x, which is the only thing that changes from one iteration of the loop to the next, and that's keeping track of the x position of the line. Okay, and we've already established that. So we just need to draw a line from x20 to x180. So the loop body in general is the chunk of code that's executed every time around the loop. So we surround it with these curly brackets in order to attach it to this loop. So if we don't put the brackets in, then only the first line that follows the declaration will be executed and will be attached to the loop. And that might cause problems if you want to do more than one thing in the loop body. So it's always good practice to surround it with brackets. The other big mistake that programmers often make when they start writing their loops, their for loops, is to do this: a semicolon at the end of the declaration of the for loop. And basically all that says is for x equals 20, x 140, go from x20 to x less than or equal to 140 in steps of 10, and then stop, because you need to keep that open because you're looping. Okay, so what you don't want to do is immediately terminate your loop with a semicolon. You need to keep it open, okay, and then whatever's executed in there will be executed in the loop. So when you build a for loop, do not put a semicolon there, and that's a very common error. Okay, so here's where we define the structure of the looping in terms of its range, its step value, and so on. Okay, so the loop declaration has three components: the counter, declaration, the termination test, and the update. So you'll notice how the components are separated within the declaration by semicolons, but like I just said, we don't have a semicolon here. Okay, and this is important. You have to keep these three components separate. So let's look at the counter declaration first, which I've highlighted here. For any for loop, we need a single variable to keep track of, and this is what we call the loop counter. And we only need, indeed we can only have one of these within the declaration, and it will always be an integer, and there's no exception to this. Okay, here we just call it x. So we need to declare it just like with any other variable. So we declare an int variable called x, and we can initialize it straight away when we declare it by saying takes the value 20. Okay, now please note that x is local, what's called local to the loop. Okay, so because we declare x inside this loop, as soon as the loop finishes, as soon as the loop terminates, this variable essentially evaporates. Okay, it disappears, it's no longer available. So the value that we give our loop counter depends on what we're using the loop for, and if we're just counting things, then we often start at 0. But here the loop counter not only allows us to count the lines, but it also allows us to place things, in this case the line. So it serves a useful double purpose. But the important thing to remember is that counters don't just have to go up or down by 1. So here we see the termination condition. So the termination condition tells us when to stop looping. Okay, and basically the for loop keeps looping while this condition is true. So long as x is less than or equal to 140, the loop keeps on looping. And termination conditions are the reason why a lot of software seems to crash or hang. Essentially, a termination criterion isn't being met. Okay, so your program is just looping forever. So it's very important to make sure that you get the right termination conditions, because if the loop is ever to have a chance of stopping, then we need to change the value of the counter so that it eventually does hit the termination value. So for this we need to update the counter. And this is how we vary the value of the loop counter from one iteration to the next. So this is essentially a pattern. Okay, this is the start value of the loop. This is what we need to terminate the loop, and this is what we do every time around the loop. We do the update. Okay. Now often we just want to add 1 to the loop counter, but here we want to go in steps of 10 pixels, so we add 10 to the loop counter. So here we do it explicitly. We say every time around this loop, x takes the value of whatever x currently is plus 10. Now we can also say x plus equals 10, and we'll see that shortly, which is just a shorthand way of saying the x increment is 10. And if we just want to add 1 to x, we can say x plus plus. Okay? So we aren't restricted to adding to the loop counter. We can also use any arithmetic operation like subtraction generally to the loop counter. So just as an aside, the x plus plus is how the language C++ got its name, because it's an incremental version of the original C language. So now that we know all of this, how do we translate this circle pseudocode into processing code? So I've included the for loop for the previous example, the lines, just to give you a sort of template. Okay, and what I want you to do now is basically pause the movie and try to write your own for loop to replicate this pattern, okay, based on the pseudocode that I've described here. So here's our code, and here's the code aligned with the pseudocode. So the first part talks about the range and the update here, the range of the circles, if you like. And here's how it's converted into processing. So we declare an integer variable in our for loop called diam, which is the diameter of the circle that's being dealt with this time around the loop. Okay, and we give it an initial value of 120. Okay, and as long as diam is greater or equal to 60, which is what we say here, okay, and it goes down in steps of 30, so diam equals diam minus 30 in this case, so we knock off 30, so it goes basically 120, 90, 60, and then next time around the loop it will go to 30, and it will never enter the body of the loop because obviously 30 is not greater or equal to 60. Okay, so as soon as it hits 30, the termination condition is no longer true, and it exits. This is how we relate the value of diam to the color. So you'll remember that for each of the 3 RGB components, when we specify a color, their intensity or the strength of the color is expressed in terms of the range 0 to 255. So 255 is the most blue, the most green, the most red, and 0 is the least. So if we dial down the values of red and blue, okay, and only focus on the green component, then if we start with a value of 255 for green and then subtract the diameter from the maximum intensity of 255, then the green component value goes up as the diameter goes down. So if we think about it, if diam starts at 120, then 255 minus 120 is 135. Next time around the loop, diam is 90, so 255 minus 90 is 165, which is obviously greater than 135. And then next time around the loop, diam is 60, so 255 minus 60 is 195, which again is more intense. So you can see how you relate the diameter of the circle to the intensity of the green component. So we use this value for both the filled region and the stroke, the line that we draw around the circle, so there's no sort of discernible border between the circles. But we might achieve a slightly different effect by maybe changing what we do with the stroke colour, the line around the circle, maybe subtracting an extra 10 or whatever. Try it and see. Just experiment and play with it. and here we actually draw the circle. So you'll notice how we can access the loop counter diam directly inside the body of the loop, and that allows us to essentially draw the circle that is determined by the loop counter, which is here.